Hurricanes rank amongst the most dangerous storms on Earth. They inflict losses of billions of dollars each year. Only the forecast helps save society from the worst of their impacts. Yet despite constant international scientific effort, we still don't understand their most dangerous shifts of mood. For a hurricane can explode to extreme and lethal strength in just a few hours, and nobody fully understands why. Each year, the tropics undergo trial from the most powerful storms on the planet. Worldwide, they go by different names. Typhoon in the Pacific, cyclone in Australia, and in the tropical Atlantic, hurricanes. All are names for storms born from almost identical circumstances. All have the unique visual signature of a disc-like storm system, rotating around a calm eye of extremely low atmospheric pressures, with winds accelerating ever more viciously towards that center. All are potentially deadly. Minimizing their impact is a task that lies at the heart of hurricane research at NASA in the United States.
We need to understand how hurricanes form and how they intensify so we can predict them. So we need basic conceptual understanding so we can make practical forecasting tools. No one is going to forget that in 2005, Hurricane Katrina hit the United States and killed almost 2,000 people. But this is a worldwide problem. We should all care about this.
The cost of major storm landfalls can be staggering. In Honduras in 1998, Hurricane Mitch made 1.5 million people homeless. More recently in the USA, Hurricane Sandy had an economic cost of over $68 billion. The University of Miami is directly in the hurricane firing line. Scientists here are acutely aware of the need to improve the forecast.
Hurricanes are part of nature. They occur. Some are not so severe, some are very severe. For us, it's an important geophysical phenomena that occurs in nature. We would like to understand them more, and by improving the understanding, we improve the models.
The models are simply numerical representations of nature that attempt to predict the weather and are core to Joe Sione's research at NOAA's Hurricane Research Division.
How do these models work? Well, it's code, it's math, it's physics. The physics that's used in these models, though, make a lot of assumptions called parameterizations. A lot of parameterizations in there were developed decades ago. Guesses, if you will. Good guesses maybe in some cases, but guesses nonetheless. The end game is improving our ability to predict this phenomenon.
The very first of those guesses in hurricane prediction was made in Cuba. Jose Rubiera, director of the Institute of Technology Cuban Weather Service, is the latest in a line of forecasters that began in 1875 with Padre Viñez.
He was a big figure, a member of the Cuban Academy of Sciences, a forecaster of hurricane. He was the first ever in the world who issued a hurricane warning on September 1875 in Havana, Cuba. It has been authenticated as the first hurricane warning in the world. So when he died in 1893, he had written 2 books about hurricanes, and one of them was a complete theory about the structure of the hurricane and how to forecast a hurricane with the means they had at that time. But they didn't have satellite nor anything more.
With almost no meteorological data, there was little improvement in the forecast prior to the formation of the National Hurricane Center in Miami in 1956. Even then, there was almost no way of observing hurricane formation over the ocean. But all that was set to change.
Some of NASA's first launches were weather satellites in the 1960s, including a satellite that had an infrared camera. That infrared camera let us see the world in a new way. Never again would hurricanes take us by surprise. And ever since then, we've been launching satellites with infrared cameras. There's a fleet of them circling the Earth in geosynchronous orbit.
There are as many as 3,000 in orbit. Among them, the workforce of weather satellites, part of the high-tech scientific effort to research and improve the hurricane forecast. Better prediction of storm direction of travel has resulted from radical refinements in observing systems, tools that sharpen the forecasts at the National Hurricane Center in Miami.
The accuracy of the National Hurricane Center track forecast has improved greatly over the past 20 to 25 years. So much so that we've actually cut our forecast errors by more than in half over that time period.
But what they don't do a good job at is that rapid intensification. The computer models are not yet consistently and accurately forecasting rapid intensification or rapid weakening, and the forecasters can't do that either. So we've got a long way to go there.
Rapid intensity changes are still capable of catching forecasters by surprise, risking serious consequences during hurricane landfall. With populations in the Caribbean and coastal U.S. expanding at well over 300 million people, the need to predict the storms more accurately is ever more pressing.
With the increase in population, it takes more time for these people to evacuate and move out ahead of a storm. So it requires better and better hurricane forecasts to try to refine these hurricane warning areas and also the areas in which people need to evacuate from.
Hurricane Sandy is remembered for its massive impact on the northeast U.S. coast. But earlier in its path, this was a storm that underwent rapid intensification prior to landfall in Cuba.
Sandy was not a surprise. We made a good forecast. Sandy went from the Category 1 hurricane to a Category 3 hurricane only 17 hours. So it was a very fast increase in intensity.
When it passed over Cuba, Sandy was a major Category 3 hurricane. But at landfall in the USA, it had weakened to a Category 1 or less. Even then, its size and the effects of the storm surge wave heights caught many by surprise.
This is the back of our safari ride. As you can see, the water came out from underneath the boardwalk and took up all the piling, all the boardwalk ramps, and did some pretty good damage into this ride and the pier that's connected to it.
10 to 15 seconds, it'd be gone. It was like going about 50 miles an hour heading south. something I've never seen before, and then I realized that there was some real destruction going on because I'm seeing almost whole sides of houses going past my house in the ocean.
What I saw was 3 foot of ocean water coming down both sides of the street. After looking at the waves for 10 minutes, I realized that all the oceanfront homes were going to get punched out.
You know, there wasn't very much rain. The rain was very light, but the wind was absolutely incredible. You know, I've never, ever, even with all the other hurricanes that have, you know, come through, Irene, etc., I'd never seen the ocean quite like that.
Sandy left an indelible imprint on the consciousness of the USA. But although huge in size, it was barely a hurricane when it struck land. It is the probability of a similar-sized storm undergoing rapid intensification prior to landfall that haunts forecasters.
Kind of one of our nightmare scenarios is to have a storm rapidly strengthen as it's nearing land because it can increase the amount of surge, storm surge, the amount of impacts from wind, the stronger the storm get.
Bursts of rapid intensification are common in many of the most famous storms, like Camille in 1969, Katrina in 2005, and perhaps most famous of all, Hurricane Andrew in 1992, which leapt from a tropical storm on August 22nd to a Category 5 hurricane at landfall just over a day later.
Loosely speaking, though, rapid intensification could be 20 knots in 12 hours or something like that. In fact, some of the most famous storms that rapidly intensified, like Hurricane Andrew in 1992, intensified huge, 45 knots in just 12 hours. That's rapid intensification for sure.
With little advanced warning, Hurricane Andrew crashed into South Florida and left the unprepared city of Homestead utterly demolished in its wake. The scenario that NOAA's hurricane hunters try to ensure never happens again.
If you told someone it was going to be a Category 1, maybe they would decide that it was okay to stay on the beach and not have to pull the boats out, etc. And if it shows up as a Category 3 or Category 4, literally the storm surge could overwhelm the populace and destroy the boats, the houses, etc. And it could be quite devastating to those people and for the forecasters themselves. No one would believe you the next year.
Each and every day as a forecaster, we come in and we assess what our needs are for flying aircraft for the next couple of days. If there's an area of disturbed weather that might form into a tropical depression or tropical storm, we will task aircraft to go out and investigate that area of disturbed weather.
The only way to get data where on our terms, meaning that we want to collect it, is to go there. For decades, we've flown into the eye of the hurricane.
Most of the time, the path that we take to the storm is the direct path. This plane is fast enough, strong enough, and can take pretty much anything, so that we want to be as precise as possible. We cut a straight path. We only deviate if we absolutely have to, and we do on occasion. Well, the principal role of air ops, or actually flying in the storm and the hurricane, is to actually get what they say is in situ measurements, or measurements in the storm itself, and we can report back to the National Hurricane Center what's actually occurring in real time in the storm itself, because satellites just can't see down through the clouds and the rain. You actually have to send an actual person in, and we do it here in this vehicle called a P-3 Orion. Well, the real-life experience of rapid intensification is that you brief, and during pre-flight, you'll spend 2 or 3 hours preparing the plane and briefing with the scientists. You'll expect one level of storm, and usually it's lower, and then you get to the storm and you have something that's quite a bit different, quite a bit stronger, and usually growing. You know, one of the worst scenarios you can be in is a tropical storm trying to be a hurricane, which can be quite painful.
The hurricane hunters ride the hurricane for as long as their fuel load safely allows them. The data they obtain helping to form a picture of the storm's state of health. What exactly makes a healthy hurricane? The first ingredient is tropical heat over an ocean. So hurricanes are beasts of the tropical Atlantic, Caribbean Sea, and the Gulf of Mexico. Many of the storms have their origins from weather disturbances coming off the coast of Africa, called African easterly waves.
Now, most of these systems that come off Africa do not become hurricanes. I would say somewhere on the order of 9 out of 10 do not. So you have to have a lot of things right for it to occur.
Between May and November, these African easterly waves progress west across the Atlantic every few days. The next ingredient is a warm ocean, with sea temperatures of 79.6 degrees Fahrenheit as the usual trigger point. Air in the form of wind blows across the oceans from regions of high atmospheric pressure to low. As the tropical disturbance travels across the ocean, the winds evaporate heat and moisture from the seawater. The warm, moist air forms more and more thunderstorms, with the air inside them rising upwards by as much as 60,000 feet.
So as you get this warming, you get pressures that reduce. And as the pressures start to reduce, you start to get the winds start to accelerate towards this incipient disturbance.
The winds rush faster and faster towards that low pressure and the growing thunderstorms, which pump hot air into the stratosphere. When that low pressure storm core becomes sufficiently developed, the weather system starts to be influenced by planetary forces. The storm is now ready to grow through the different stages, to metamorphose into a hurricane. To measure the strength of the growing storms, the forecasters categorize them by wind speed. As a Category 1, it will only have sustained winds of between 74 and 95 miles per hour. As a Category 5, it would need winds of over 157 miles per hour. With the strongest recorded hurricane having winds sustained at over 190 miles per hour. The storm's fate will be determined to a large extent by atmospheric winds surrounding the system. If they are at different speeds or directions at different heights, they will prevent the storm from growing.
What happens? The storm tends to tilt over. Think of it getting decapitated. It doesn't like that. It wants to remain vertical.
This difference between wind strengths at height is called shear. If the difference is large, the shear is high and will cut the storm to pieces. If the shear is low, the storm can grow. Once in range of the P3 Orions, the NOAA hurricane hunters fly research patterns back and forth through the storm. Measuring atmospheric conditions within a hurricane is vital to determine if wind shear is suitable for intensification. For that, they need to put instruments into the storm itself.
So we developed this technology, this drop-son technology. It has sensors here for pressure, temperature, winds, and humidity. And as it drops from the plane, falls down, and within 2 to 3, depending on the altitude we fly, hits the water.
But in those few brief minutes, the sons record vital, precise observations from the very worst conditions in the weather systems below. During the flight, they drop many hundreds of sons into the hurricane. As they fall, each of them transmits weather data back to the aircraft.
Think of it as a picture, a snapshot. It gives us a profile, but where the winds take it tell you where that profile is. So it's not even a vertical profile.
The data profiles help to locate the eye, the very center of the storm, where weather conditions are completely benign.
When they say hurricane hunter, what you're doing is you're hunting the eye by keeping the wind at your 90 degrees. So as the wind changes, you change the nose of the aircraft until you find the exact center of pressure, low pressure, and the lowest winds, which theoretically are 0.
This is also where the most vital core of the growing hurricane is found, the eye wall, the narrow band of intensely convective thunderstorms that encircle the central low-pressure eye.
The part of a hurricane that energetically is, I would say, the most important is the eye wall. So just beyond that clear eye, there's a ring, or at least an arc, of strong storms. And it's there in the eye wall that all of the mass that's circling in at the surface and then spiraling out at the top, it has to pass up through the eye wall. In fact, it's just sometimes updrafts half a kilometer across.
The system is by now a weather heat engine. Warm air, in the form of increasing winds, spiral towards the eye, where they encounter the convective thunderstorms of the eye wall. The winds are swept high towards the stratosphere, where they radiate outwards for thousands of miles.
I think of a hurricane as a marathon runner, and I think of thunderstorms as sprinters. They're fast, but then they have to stop. So a hurricane can keep going for weeks, as long as it doesn't hit land and lose its oceanic energy source.
But a hurricane is an unpredictable beast that can change intensity in a matter of hours at any time. To try and predict those changes, research scientists build complex computer programs. When observed weather data is put into these mathematical models, they can calculate future weather trends. But it is far from simple. NOAA's Hurricane Research Division tests models in development to ensure their value for improved forecasting.
One of the techniques that we're using here at the Hurricane Research Division to improve the accuracy of the models is to increase the resolution of the model.
Our track forecasts have improved greatly during that time, while our intensity forecasts have not improved as much. And it's because in track forecasting, the tracks of storms are more governed by these large-scale features in the atmosphere. These very large high-pressure areas or low-pressure areas help to steer the storms, and that is fairly easy to model.
Increasing resolution has allowed modeling of hurricanes in sufficient detail to predict the atmospheric steering of their tracks.
As these computer models have gotten better and better, they've been able to see these large-scale features and know how they're going to move over the course of the forecast period and how they're going to evolve and where the storm may go.
The resolution hurricane model impacts how we are able to resolve processes happening inside the hurricane.
Ultimately, the credibility of the forecast depends on being able to predict rapid changes in strength. The question is how? Why is it that improving field observations and computer models are working better for track forecast, but still fail fundamentally with rapid intensity? So the first step to understanding what processes drive rapid intensification is to improve the fine detail of weather data. And for that, you need to get down and dirty. Scientists realize that the best approach is to venture into the storm's heart, equipped with high-tech specialized instrumentation. The University of Florida's Hurricane Research Team is led by Forrest Masters.
So for many of you, this will be your first time traveling into a hurricane. I need you to listen closely. We're going to push hard to intercept the storm. It's absolutely imperative that you follow my instructions, stay vigilant, and let me know if there's anything that's going to prevent us from collecting data or creates an unsafe situation. So weather deteriorations, they're going to deteriorate quickly. Just stay alert. Let's get to work. Deploying on such short notice creates a lot of logistical issues. We have to think about fuel, where we're going to set up, where we're going to lodge, what's our evacuation strategy. We have to make all decisions on the fly. Generally, as we're driving into the storm, most of these decisions get made. Once we leave, we drive directly into the storm. Using aerial imagery and local knowledge of the area, we deploy the equipment and sites that are expected to be in the worst winds.
As Hurricane Isaac threatened a first landfall over the Florida Keys, Forrest and his team raced to get the instrumentation in the path of the eye.
Data are scarce in tropical cyclones worldwide. If we look specifically at the United States, there have been significant historical moments where we've had a major event and we've had very little data to rely upon post-event. So even today, when a storm happens, it's very unlikely that we'll have intact wind speed records from the fixed weather stations that are out there. So we have this specialized mesonet, which is essentially a collection of weather stations that we deploy in the path of the landfalling hurricane. And this gives us the high fidelity information we need to reconstruct what happens at landfall. We work using portable instrumented towers that have specialized instruments that characterize the speed of the wind and also the diameter of the rain particles. The importance of this technology is it allows us to reconstruct the rain intensity, which we can compare directly to the wind speed at that particular site. And so for the first time, we're able to look at how do the winds and rain evolve as rain bands and other features move through the impacted area.
The storm barely brushed the Keys before heading across the Gulf towards Louisiana. With over 1,000 miles to drive, Forrest's team were up against the clock to catch up.
We have very few chances to conduct these experiments. We have to seek out the most heavily impacted areas, which always brings us in the vicinity of the eye wall. We're looking for the radius to maximum winds, and that's the distance from the center fix where we expect the most severe winds to happen. Hurricane Isaac is a very unusual storm. It intensified right before landfall. Now it's moving through, and at the speed that it's moving, it's going to take some time before it leaves the area. Isaac presents a fantastic opportunity for the research community. There are literally dozens of assets spread across the state right now collecting data. Many of these are co-located, so we'll be able to go back, look at what's going on aloft, and be able to compare to what's going on below. This is a real first for our field.
Teams of scientists gathered precise high-resolution wind, rain, and Doppler radar data directly under the eye of Isaac. Analysis of such events will give greater understanding of the small-scale features that create the structure of the hurricane's eye.
These data are used by many disciplines outside of engineering, including meteorology, hydrology, and other fields. For example, the type of wind-driven rain data we're collecting can be compared directly against the predictive models that are used to predict the rainfall deposition in an area using radar information. Ultimately, we are strengthening the knowledge base by going out and collecting information that really simply doesn't exist. And over time, through more and more storms, we'll build a large database that we can turn back to hopefully develop better predictive models.
Even with more intimate data sets, opinion still varies as to what exactly drives intensity change. Nick Shea of the University of Miami explores the impact of ocean water temperatures. He sees a strong connection between sources of warm water and intensification.
The detailed focus of our research with hurricanes is trying to assess what is the role of the ocean in rapid hurricane intensity change.
Sea surface temperatures are a measurement of the outer skin of the ocean and no indication of water temperature at depth. So Nick and his team mapped deep warm water areas that extend many hundreds of feet below the surface. Called warm pools, sumps of water hotter than 78 degrees Fahrenheit and up to 200 miles in diameter. They are vast reservoirs of heat energy for passing hurricanes. In the northern Caribbean, numerous deep warm pools calve off from the currents of the Gulf of Mexico Loop and the Gulf Stream. NOAA flies Nick and his team to research any hurricanes heading for a warm pool. They drop special submersible sondes that transmit precise data from hundreds of feet underwater. Information that shows what happens when a hurricane crosses a warm pool. The result is chilling.
And then subsequent to Andrew, there was a major hurricane in the Gulf of Mexico that directly went over a deep warm pool, and the name of that storm or hurricane was Opal. Opal went from a Category 1 to a Category 4 storm in 14 hours, rapidly intensified, and became a very strong storm in the Gulf of Mexico, right over one of these deep warm pools.
The storm spelled disaster for the people threatened by landfall in the northern Gulf of Mexico. Only the fact that Opal weakened on crossing colder water saved them. Nick and his colleagues are convinced it is vital to know exactly where the warm pool features are when a hurricane threatens landfall. October in San Juan, Puerto Rico. Oceanographers are not alone in their interest for warm pool distribution in the ocean. Sport fishers preparing for the annual San Juan International Fishing Contest. In search for ever-improved data to pick out where warm pools are, Nick Shea has begun a new collaboration to take advantage of a most unlikely ally.
It turns out that my colleagues here at the University of Miami like to tag fish species like blue marlin.
The satellite tag technology helps them find out more about oceanic fish behavior.
One of the areas of fertile research that are currently going on here at the Rosenstiel School, where we're actually tagging fish with temperature sensors, and as they go down looking for food and come back to the surface, they actually send temperature profile data back to the satellite that we can pull in to help us look at these, look at the temperatures. And the beauty of the fish is that they can actually swim against the current, where we actually need the data the most, because that's where the deep warm pools are.
Marlin seek the 79-degree temperature gradient around warm pools for very good reason.
The blue marlin love to be in the vicinity of these deep warm pools. Along these deep warm pools are areas of upwelling. In other words, cooler water is coming to the surface. These are smaller scale ocean features where there's a lot of food for these marlin and these sport fishes to feed upon.
The object of the game is to catch sport fish and attach satellite tags before release. The tags record information that may be invaluable for the ongoing search into the causes of rapid intensification.
We have a case where we had Hurricane Ivan. There was a tagged blue marlin on July 3rd, 2004. So this was before Katrina. It turns out that this one blue marlin was just lingering around this big warm core eddy right on the perimeter where the cooler water was. And what happened was during the period that he was in the northern Gulf, Hurricane Ivan came into the Gulf of Mexico in mid-September. So as Hurricane Ivan moved towards the north, This blue marlin went actually underneath the track, and we actually have a couple of profiles characterizing the upwelling or the cool temperatures that the fish saw where all this upwelling was occurring. And when I say upwelling, it just means colder water is coming towards the surface. It's very clear the ocean is playing a role in intensification. Now, you might want to argue how much.
Now forecasters do take ocean temperatures into account for predictions, but many researchers believe the causes of intensity change lie elsewhere.
The specific area that I'm very interested in is looking at how the enormous amount of energy that's stored in the ocean when we think about hurricanes, how does that energy get to the atmosphere? I think the air-sea interface in a hurricane, particularly in the high wind region, is critical. So if this is our ocean, this is our atmosphere, we're talking about an area that's very close to the surface of the ocean and, say, 30 feet or 10 meters above the ocean. This is the area we're talking about. This is the traditional way we calculate flux. That is, how much energy, either heat energy or, even more important for a hurricane, moisture energy gets out. So that is determined by the thermodynamics of that gradient.
Heat energy moving from the water is governed by the humidity of the air above it, and Joe believes that if the saturated air at the center of the hurricane's eye gets slightly drier, it will be able to absorb more water and heat from the ocean.
So if you can have a change in relative humidity, which looks pretty benign, 95%, 90, still pretty humid, right? That type of difference in high wind conditions can be a tremendous boon to the storm as far as intensity change goes. You could be looking at energy 30, 40, 50% more drawn out of the ocean than otherwise would have been the case. And if you have that situation over several hours, you don't need a lot of time. If you're looking at 5 to 6 to 10 hours, that can be the difference between a Category 1 and a Category 3 or Category 4.
The wave tank at the University of Miami helps Joe observe the saturated conditions that wind and waves create immediately above the ocean surface. He believes a very small drop in humidity from downdrafts will fundamentally affect the energy flow.
That will change that gradient, that vertical gradient, and allow more moisture, more evaporation to get out of the ocean, just enough to really make a difference in the storm structure. By changing how much energy comes out, we also can change the actual intensity or the wind speed of the storm. So that change in energy, if you're changing the energy by 30% or 40%, you're essentially allowing the system to jump from, let's say, a minimal hurricane, 75 miles an hour or so, to a major hurricane well over 100 miles an hour in a very short amount of time.
Proof of the theories for rapid intensification require better data. At Wallops Air Base in Virginia, scientists from NASA prepare a revolutionary observational platform to provide just that, the Global Hawk.
The Global Hawk is really an incredible airplane. It's a combination of both an airplane and a satellite. It flies at about between 60 and 65,000 feet. That's about twice as high as a commercial airliner. It can fly over 10,000 miles, or about 12,000 miles actually.
Of key interest is obtaining observations of a storm over enough time to be able to capture the processes that drive rapid intensity changes. With a flight time of over 36 hours, the Global Hawk is a big step forward towards doing that. The entire research and flight team are ground-based. Scientists will monitor data coming from the aircraft in real time throughout its mission. The pilots prepare the Global Hawk for a flight across the Atlantic Ocean and back. Yet it will still conduct nearly 24 hours of research time over the storm.
One Global Hawk is equipped with instruments to look at the the near field around the storm, so we can look at how winds around the storm are controlling storm motion and how they might be impacting the intensification of these storms, how they change from a tropical storm to a Category 1 hurricane. The other platform has a series of instruments that can look directly through the clouds into the guts of the storm. The Global Hawk can take off from the coastline in the U.S., fly all the way to Africa, sit on top of one of these forming hurricanes for 10 hours, and then fly all the way back. Manned aircraft are simply not capable of flying that long and that far.
7 a.m. next morning, Global Hawk touches down after its mission to Africa and back. With rapid intensification still an unsolved mystery, perhaps there is one more perspective that may yet prove to be the most conclusive. Eyes from space. Scientists from NASA Goddard have been looking deep inside the hurricane clouds with a special satellite and radar. In 1997, the TRIM satellite was launched, and it has been relaying revealing data to Earth ever since.
What's special about TRIM is that this radar can measure storms from the Earth's surface up to the top of the troposphere and into the stratosphere.
The ultra-precise radar aboard the TRIM satellite emits a minute amount of energy, but it's capable of seeing the weather 250 miles below.
The radar sends its energy down in a tiny range, around 13 gigahertz, and in 1/1,000,000th of a second pulses.
But these minute energy signals are incredibly powerful scientifically. The TRIM satellite radar reveals exactly what is to be found inside the hurricane system.
The eye of a hurricane, normally you think of it as a very peaceful place. There's gradually settling winds, there's not any clouds, but the air at the bottom of the eye has been trapped there for a long time, and it's very moist, and it has a lot of energy, and occasionally it can break out of the eye into the eye wall and become the most energetic air parcels in there and ignite hot towers.
What this remarkable satellite revealed was that inside the hurricane there are areas of extremely intense updraft, super storm cells.
A hot tower is simply a storm cell that has a strong enough updraft that it's punched through the top of the atmosphere that normally contains weather, which is called the troposphere.
These dynamic storm cells explode upwards over 9 miles from the Earth's surface and into the stratosphere, so high that the temperatures are minus 112 degrees. Yet the energy of these so-called hot towers is immense.
Now, a hot tower by itself doesn't release enough energy to affect the fate of a hurricane. Put enough of them together, and you could. And so we know from these satellite observations that you can have a sequence of hot towers, one after another, sometimes just on one side of the eye. There can be a favorable region. So you'll have these mesovortices traveling around the eye wall, and when they hit the favorable region, a hot tower shoots up inside that vortex.
This convective burst on the eye wall of a rapidly intensifying hurricane is stupendously powerful. In 12 hours, it releases as much energy as the entire U.S. generates in over 2 weeks. This hurricane turbo-powered heat engine was only visible because of TRIM's unique radar view.
I feel as if it's peering into their personality, because you can't tell much from a person by looking at their face. If you have a sense of their emotions, and you get a better sense of who they are. So by seeing deep into the heart of a hurricane with TRIM, seeing every layer of it in three-dimensional detail, we get a sense of, is this storm really intensifying, or is it faking it? Does it just look like a storm about to become a monster storm?
Despite Owen's conviction that hot towers are fundamental to storm intensity, he believes the science is too complex for one simple catch-all answer.
There's controversy in what causes rapid intensification, and the answer is likely that it's not the same thing in every case.
With scientists struggling to identify the cause of rapid intensification, how reliable are the predictive models that depend on their observations? At the Hurricane Research Division, they may be on the cusp of an information technology breakthrough.
As computational power increases, we will be able to run hurricane models at higher and higher resolution. For example, right now, the large-scale fields, the large-scale environment of a hurricane model is executed at a resolution 27 kilometers. As computers becomes faster, more powerful, we'll be able to resolve this large-scale environment at even higher resolutions, such as 9 kilometers and 3 kilometers, as we currently do in the hurricane region.
As far as the numerical models, we are still a long ways away from getting to the point where we can trust numerical models to give us accurate RI forecasts. The tools we have to do so are better observations, but ultimately, from a prediction standpoint, we need to use computer models to improve our ability to say where these systems are going to go and how strong they will be.
Even so, in the uncertain world of hurricane prediction, there are some clear truths about the reliability of intensity forecasts.
You know, I don't want to sound like I'm bashing the models here, because you can't expect miracles. We really need to do a better job, in my opinion, of observing what goes on in the core of the hurricane and getting that into high resolution computer models. There's still a lot of work to be done, and that's not going to happen anytime soon.
What remains without question is that hurricanes are incredibly complex and powerful weather systems that we still struggle to fully understand, despite our commitment to science and funding. Brilliant scientists worldwide are initiating new research to try to increase the ability to predict hurricanes and get the message across.
But I think we need to look at these fundamental equations that we've used for decades and never thought to evaluate exactly in this way. Now, this is research that has not yet finished peer review, so this is what I'm currently working on.
With the causes of rapid intensification still eluding the scientific minds that struggle to unlock the puzzle, societies throughout the tropics remain at risk from cyclonic storms. It is clear hurricanes are a danger that cannot be fully predicted. And if it can't be predicted, how can the public ignore the potential dangers? Yet many people gamble by ignoring official evacuation orders and sit out hurricanes at home, which questions how fully we understand the risks involved. For hurricanes remain capable of inflicting enormous loss to property and life. The fact that some of the cleverest minds in science fail to completely understand and predict rapid intensity change renders the storms more deadly still. The percentages may be against a sudden major intensity change, but hurricanes thrive on being unpredictable. One has to ask the question, is it wise to tempt fate with the greatest storm on Earth?